A few months ago, Erin invited me to do this Python tutorial, and I asked how long it is, and she says 1 hour. Okay, I said 1 hour. Usually we would do like um, around 3 hours for this. So I'll try to think about what to put in this 1 hour, so people with different levels of Python or DICOM image processing experience can benefit a little bit. So the way I put it up here is basically have the aim. If you are new to Python, you know where to start, what to look for. And if you know a little bit of Python, then you know what tools are there to analyze this DICOM and process them. And if you are very familiar with DICOM and Python, then you probably can see some of the tools or the way of thinking that I do. So if you are at different level, you hopefully you can get something out of that. So, okay, let's get started. Oh, by the way, if you open the link, you will see a similar page like that. And this is the Colab environment. So Erin told me I better talk about something about Jupyter. So I will do that at the end of that. The reason is that Colab is already out of the box and there's no setup requirement. You can just click and execute things. So if you want to follow along, just go to File and then make a copy in Drive. What this will do is that it will copy this document. This is just like a shared Word document, but it's in like the Colab version. And then open up a new tab. And in that tab, you can start executing it. And you'll see a connect button here if it's not something like this, and you can hit the connect. And what it would do is Google provide you with some free hardware that you can run onto that. Just a sidebar, in the future, if you want to utilize some GPU, you can go to runtime and then change runtime. And then there are some GPU options there. If you pay a little bit, like $10 a month, then you can have more powerful GPU. But there will be a cap there. But it's a very good platform if you want to start Python and experimenting with some code that you find on GitHub. You can just pull directly to this Colab environment and executing it. Okay, so that's basically the setup. I'll do some introduction, and you can spend some time just make your own copy and try to execute it if you want. So Python is a general purpose programming language. So general purpose is the key word here, because you've heard a lot of programming languages like R or Stata, SAS, and some of them are not general purpose, which means they are only focused on a certain area. For example, R is focusing on statistics, and for doing small scale machine learning, that's fine with R. But if you want to do large scale machine learning or other stuff like web development, R is probably not good for that. So that's what I mean by general purpose. And Python is usually used across many fields like web, scientific computing, machine learning, and deep learning, which is one of its main strengths, and financial and some of the algorithmic trading, which is also largely explored recently. And another benefit is that a lot of software has the embedding environment built in, which means you, like, instead of clicking buttons or use your keyboard to type in things, you can automate the whole process using Python code. So it's just like an invisible hand to just do everything for you as long as you know exactly what to do. So in 3D Slicer, which is an open source tool to visualize and analyze imaging data, what you can do is down to like each button or how long you can wait and click which button, something like that. You can do very surgical movement with Python, and everything is built in. And another key feature of Python is it's very beginner friendly, which means it's very easy to learn, to get started. But to become an expert, you still need to put some effort into that. But to get, say, from 0 to 70% capability, it's pretty much quite easy compared to other coding languages like R or C, for example. So I put an example here. So for those who don't understand any Python, just look at the code and you can basically read through it very easily. So what we have done here is we define something. So you don't, at this point, you probably don't know what it is, but as a name that get the circle area, and then it calculates some number. And from simple maps, you know that's the area of the circle. And what you do is that you can provide a variable called R and assign 2 to it, and then you can, so this should be R here, and then you calculate the area using this variable, and then you can print the whole thing out. So if you execute this, so if you hit the triangle here or Control Enter, that will execute this. And if you want to execute this while having a new line of code after that, you can hit the Alt Enter on Windows. So that will execute this and then create a new line of code here. Okay, I'll delete that. So that's what I mean. It's very beginner friendly. So if you are hesitating which language to pick to get started, I would highly recommend Python. And I would say Python is probably the best language out there for you to get started. This is not only in, say, scientific computing, but in general. If you want to build some bots to do auto trading for stocks, Python is great for that. It can monitor things and do it for you. Okay, get to the topic of MRI and the DICOM. So this is basically the simple code you can do. And in the industry level, what you usually do is do something like that. And that's the production code that you would do. And that's basically quite similar to this. This is like a clean piece of runnable code. And this has more documentation, which means people using your code can have more help when they get to this function. So if we define this, and what you can do is actually get the help function on this. And what the help function would do is retrieve this, what we call as the doc string, and then print it back to you so you know how to use this function. And this is what you actually get when you use the help on some of the building function, like the Python, sorry, not the print. Yeah, this is when people wrote the code that have this as the docstring building. So you can see to call this function, what value should go in and what are the other arguments that you can pass in. Okay, so if you're a beginner, you probably don't understand all of this, but don't worry. This is probably where you can get started, and over time you just look at what other parameters are. All right, so another piece of code is here that you can say A equal to 1, B equal to 1. And then for I, which looks like some sort of iteration, we can print A. And then we replace AB to B and then A plus B. So basically AB start with 1, 1. The next one, it becomes A equal to 1, which is the value of B. And then B will equal to the sum of A and B. So what we are essentially doing here is just to get the Fibonacci sequence. And with this type of syntax, you can see how easy it is to swap two variables rather than you have, say, C equal to A and then A equal to B and then B equal to C, like this to swap the two variables. All right, so this is just another example. So one thing to mention is that there are two main versions out there, Python 2 and Python 3. So do not get confused or mix use of these two versions, because they are not backward compatible, which means when you look at some previous code, and if they are using Python 2.7, you should expect some of the lines there won't be compatible with the mainstream version, which is Python 3 now. So be careful about that. And if you find some piece of Python 2, you can either use a Python 2 interpreter on your local machine to execute that code, or you can convert the code into Python 3 using some like tools out there. There are many tools out there you can convert different versions. Why these two versions are not backward compatible is a problem of history that can be quite long to explain, but you just need to know they are not backward compatible. And if you start learning now, learn the Python 3 instead of Python 2, because Python 2 is already out of support at the moment. So to know what version of Python that you are running, you can just look at the import the sys module and you can print the sys version, and they will tell you currently the Google Cloud running now is the Python 3.10. And what we mean by Python 3 is the major version here. So whether it's 3.8 or 3.10, the difference is not that big. So if it's version 3, then it should be fine. Another great benefit is that Python supports Unicode natively. So if you don't know what's Unicode, basically it's a coding that's different from the ASCII, which is a narrower selection of coding. So Unicode can basically code all the language in the world. So which means in Python, you can not only use English as the variable, you can use any other language like Chinese or Spanish and Japanese or German, any other language. So you can assign things to the print function like that. You can print out all this and it will print out nicely. But this is just for fun, and it's much tedious to use Chinese to program rather than English. All right, so hopefully if you're a beginner, this will get you some interest on what Python looks like and what benefit it has, and that will probably like get you started to learn it. So if you know some Python, and what I'm going to talk about are some of the essential or vital pieces in Python that will build a good foundation for your, say, image analysis down the track. Because if you do not know this concept, there are some pitfalls or behavior that is very hard to explain. Okay, so the first important concept is function. So function is a recipe that's predefined by someone or by yourself and can be executed when you call it again. So in general, in a philosophical sense, function represents the dynamic components in our world. So anything that's moving, that's actionable, that can be done, we can sort of represent those things as function. Say if you want to calculate the area of a circle, that's a well-defined process, and you can wrap this up as a function like that. So later on, you can just call this function and pass in some variable to customize what the behavior will be. Okay, so that's function. I guess most people, if you learn programming before, then you know what function is. So the counterpart of function is the static variable. Although Python doesn't have the keyword static, but if you use Java or some of the low-level language, it will have some of the static, which means things won't change. And in our real-world problem, there are constants in MRI acquisition that won't change throughout the acquisition. So you can treat them as static things. So again, here I use the def to define a function, and that's the keyword in Python to define a function. And then inside the function body, that's whatever recipe that goes under that. And you will notice that there's some indentation differences, which is quite important here in Python. It's not very important in C because they use curly braces anyway, so you can tell what indent it is. But in Python, these are important. So this will tell you like what's the hierarchy in this code. So we just define print numbers and we provide them with an argument n. So what it would do is just for I in range will generate a sequence of number. So in this case, it starts with 1 and it will end as n. But because the way Python works, it won't include the last element, so we need to have n plus 1 here. This is just a Python design. It starts with 0, and it usually won't include the last element of that. So if we print that it want to print the first 10, it would just print 1 to 10. Okay, so these are building blocks. They are not very related to image processing, but this will be useful when you come to, say, wrap several steps in image processing as a function and do it in a modular way and reproducible way. This is the way to go. So try to define like efficient, modular, self-contained functions to do each of the key steps in your pipeline. Another key feature, or not key feature, but sort of the key concept which Python support is OOP, Object-Oriented Programming. This is quite an advanced concept, but I want to make it simple is that usually in a non-OOP language, we sort of treat the static and dynamic components scattered around. So this is like you have some files, and say you have a book and the first page is in your living room, but the second page is in your bathroom. And this is how, if we do not use OOP, what will happen is that you need to be responsible to know where these pieces are when you come to use it. So what OOP offers is a way to glue things together. So it's like you put the book into, say, an order like a real book, or you put different files in a folder. So things are wrapped together and they sort of tie to a object. And then comes the key question, which is basically everyone learns programming will ask, what is an object? So an object is just a thing that in everyday life we have a thing like a pen, a cup. So that's a thing, okay? And what the object OOP does is basically to wrap the static part, which is like the name and occupation of a person, and the dynamic part, which like introduce behavior, introduce himself, herself. This is the dynamic behavior under this person. So why is this important? Because when we look at DICOM, when we look at an MR data set in the future, or we look at some deep learning like a data generator, so all of these are objects. And if they are objects, then you need to know they have certain static information held inside this object. And also there could be some dynamic or actionable behavior inside that. And in programming terms, we call the static thing properties or attributes. They all mean the same thing. In machine learning, we call these features, and they all mean the same thing. And the dynamic part, if it's outside an object, we call it a function. If it's inside an object, we call it a method. So a method is just a function that ties to an object. So if we initialize this class, so class is like the blueprint of an object. So it's like the blueprint of a house. We can have one blueprint, but we make multiple houses. And then this defines the blueprint. And now it's time to make some house or make some person in this case. So we say P1 equals to person, Mary Jane, and I'm a movie character. And then what it would do is it would tell you she's a movie character, girlfriend of Peter Parker. Okay, similarly, you can define everything in your own language. This is just for fun. Python is very fun, and usually spend some time explore the fun part of that. You can do everything in Chinese, and still you code in Chinese and you output Chinese. Everything is fine. All right, I think this wrap up some of the key essentials of Python, which I find is probably the most important thing. There are other important concepts. You should learn the data types. You should learn the control flows, like the for loops, while loops, if else statement. But those should be quite straightforward. But these few things that are listed here should be quite important, and they are quite difficult to understand and usually need some time to grab the idea of that. by pointing out here. So along your study, you can sort of make good use of these concepts. All right, so we get to the sort of the more application-wise of Python. We'll look at what's the scientific ecosystem, and this is another benefit of Python is that not only the language itself is beautiful, elegant, but also there are many people ahead of us that have written like many libraries which are very useful, and usually you will rely on those because we are all stepping on now we are standing on the shoulders of all these giants. So Python has the philosophy of battery included. In addition to the built-in data types, which is like these strings or floating point numbers that we see in here. So these are built-in data types. Python also has some standard libraries. When you install Python, it will be shipped with these libraries. And apart from that, you can also install third-party libraries and usually use a package manager. The default one is pip, P-I-P. We'll see that later, to install third-party libraries into Python. So when we say library or module, it's a mysterious word. What is a library? And it's just some piece of code that other people has written, and you can just use them. And the interface is to import that person's code as a module, as a library. So there are many out there, but I want to point out the most important one is NumPy, stands for numeric Python. And the most important data structure inside NumPy is ND array, stands for n-dimensional array. And why is this important? Because in scientific world, we face, or mathematics or physics, we sort of face the ultimate problem is to represent data with different dimensions. Say we have a point and we use, that's the 0 dimension, and we have 1 dimension, then it's a vector, 2 dimension, it's a matrix. 3 or more dimension, we have, that's a, in some language, we call it multi-dimensional matrix, or in general sense, we call it a tensor. Like in TensorFlow or in PyTorch for deep learning, we call it a tensor. So all these ideas are quite similar, and NumPy is probably the first library out there that offers the capability to handle an n-dimensional, any dimensional actually. So n can be very large, n-dimensional data type natively. So under the hood, it uses C and C++ to do the calculation, and it has the Python interface where you can call these functions or data types. So surrounding NumPy, there are many other libraries built on top of that. So you probably have heard some of them. If you want to do some fitting optimization, simple optimization, use some Fourier transform or scientific functions, then you should use SciPy, Science Python. And if you want to do simple machine learning, not deep learning, like random forest, support vector machine, right? So if you want to say, look at the correlation in your MRI signal between different modalities, then you can use, say, scikit-learn to explore some of these correlations and wrap it out as a machine learning model. And if you want to do some image manipulation, this is not related to medical imaging, but in general images, then you can use skimage, scikit-image. So what I do here is just to show you, you can use the scikit-image to read things into NumPy, and then you can then plot it out. Okay, so the first thing we do is import NumPy as MP. So this as will basically, it's like import NumPy, but we'll give a short name as MP because we don't want to type NumPy all the time. And then we import skimage. And then we just download this file. So if you look at this link here, it's just the Python from the Python website. Okay, so what we can do, and by the way, if we use wget, because this is a shell command, it's not Python code, so this is not Python code. So if you want to execute some shell command, we can put an exclamation mark at the beginning, then we can do all sorts of shell commands here, like ls, that we can look at what data are here. So just do some exploration. You see it's quite messy, but if you do it on yours, you will see it's quite clean. And this tab will actually show you what files are there. So what we've done is to download this Python logo, and it should be here. So Python logo. I've downloaded it before, so there's an extra one, but you should have just one if you run it once. And then we read it as an image, and then when we look at the type of that image, that will tell you it's a NumPy ND array. So NumPy ND array is sort of like the currency in scientific computation. If I want to swap some rice with some, say, paper, I need to use money. So that ND array is like that money, like the currency that we use to trade things. So usually in the workflow is that you will read things into NumPy array and then do processing and do, say, machine learning or deep learning and then get the result. So everything from after reading, basically it will be a NumPy array. And then you can look at the shape of that. So in this case, it's a RGB. So this is the height and width. And then the form is RGB plus alpha channel to mean transparency because it's a PNG file. And then we can plot it out. So we use matplotlib to plot it out. And then we get the same image as what we see before. So that's how you can read the image. And then usually you don't just plot it out, but you do some, like run some filter on these images or process on this image, and then you save the data. But this is to showcase that you can read things as NumPy and then just plot it out. So make sure everything is read correctly. Okay, I think so far we've set the big picture. We know Python is powerful. We know at the center sits NumPy, and then surrounding it, there are satellite, like secondary libraries, I would call it, that does different things. And this library sort of stem out into a new branch. That's the deep learning one, which can be another like big universe by its own. But a lot of the ideas like PyTorch is basically can treat it as NumPy with some extra functions inside it. So it's NumPy on stereo. So it has autograd, which means every new variable has the history knowing where it comes from. So it can do the auto differentiation, because everything in deep learning is about knowing the gradient, and it supports GPU, while NumPy is mainly on it. It should not say many, but it's only in CPU. But a lot of the idea is similar. So in the PyTorch, you can also call the shape and the max, the min function to get the maximum and minimum value. So that all sort of inherits from the NumPy design. All right, so we are moving more into more specific things. We look at DICOM, which is coming next. So in this 1 hour, I want to show you some of the tools that you can handle DICOM, and then this will contain like generic reading and output, like input, output, and also more surgical things like how can you construct a DICOM from scratch. So if you work with DICOM every day, then you probably can learn a little bit. I'm not an expert in MRI, but I deal with MRI data all the time, and I'm mainly on the data processing and deep learning, machine learning side of it. Okay, so first of all, we can retrieve one data. What I've done is I put some data on a previous GitHub repo, and we can just retrieve that using wget, which will download it directly to the Colab server. And another great thing about this Coda environment is it's server-to-server communication. So if you got some data that probably is somewhere in another server, you don't need to download to your local machine, then push it to this Colab environment. You can let Colab just do it directly. So wget or curl is the command line tool, which is great for these purposes. All right, and every field has a hero. So we have NumPy out there, and in this domain, the DICOM domain, the hero is PyDICOM. PyDICOM still use NumPy to handle the data, but it offers some other capability to wrap around, to represent the DICOM using objects. So if you want to work with DICOM alone, like use DICOM in vacuum, just look at what information are there and de-identify the information, for example, just use PyDICOM. If you want to work with other DICOM images, like do image registration or run some filter, then simple ITK is the tool for it. But all of these are sort of quite related to NumPy array. So knowing more about NumPy array is definitely a great fortune for your future if you want to do a lot of data processing. So we install PyDICOM. So I've already installed it in this session. For you, you will see a longer like output here. And so this is the pip. You can use pip install to install a third-party library. There are many other tools out there, and for reproducibility, you should use a more advanced package manager like Poetry that will just lock in not only the package itself, but also the version and also the exact URL where that file, the will file, is downloaded. So will file is just that Python package file that it downloads and install. All right, so here for simple demonstration, we use pip to download it. And then we can import PyDICOM, and then we can read this PyDICOM. So read the DICOM using PyDICOM, and we store it in a variable called DCM. So DICOM basically has two parts, the header information for metadata, and also the image itself. So the reason it has two parts, I guess if you work with MRI, you know much better than me, you want to attach the metadata with the imaging data. So that's back to that idea of gluing things together. They should not be sort of stored apart and you have some risks of missing one piece from the other. So if we print this object, so everything now is read into this DCN object, it will print the header information in a very sort of long output here. And the header is grouped as the group and element, and also has a tag name that you can see from this. I guess you should be quite familiar with this, so I won't emphasize more. But what you can do with this DCM is you can retrieve this using this tag name, like as a property or attribute, you can do it. So that would tell you the patient ID. If you look up patient ID, it will be this one, and it will just get you the string value of this. Another way is that you use the group and element in a tuple. So a tuple is just a sequence of data in Python like this, and it's not changeable. So that's called a tuple. So we can do things like this and retrieve the same piece of information, but this time it returns that object like a slot of that header. So if you want to get this as a string, like what this one output, you should get the value attribute of that. So they will get this string and return the string to you. Okay, so you can also combine this as one string and just do something like that. It will just do the same thing. So that's basically how you can retrieve things from the header. You can also write things to the header as you want and just override things to the existing DICOM and probably save that DICOM as a new DICOM. So that's all possible. And you can also replace the imaging data as well, because that's just one slot in this. So if you think of the DCM as a key and value pairs, and these are just the keys, and the values are just what's inside this. And you will see at the end of this the pixel array, which will have the imaging data contained inside it. And this should be, if you multiply the column and rows, and you should so end up with the same elements here. Okay, so one thing that you usually want to ask is that we know DICOM is very complex. DICOM, so what we're talking about is just the DICOM format itself, but in fact, DICOM is a standard, it's a format, and it's also like a transport protocol. So there are three aspects of that. So one thing we want to do is sort of get to the conformance of, like, we should know which DICOM tags are standard DICOM and which are some of the manufactured DICOM headers out there. Because when there's a machine, that the manufacturer will put can put some of its own DICOM header information into that. So one way to look it up is that you can use the data dict. So under PyDICOM data dict, you can sort of say whether that's standard DICOM. So let's say patient ID, and it will say it's true. And then let's say patient address. Does it store the patient address? Yeah, make a guess. So we store patient address. And it's actually part of the standard DICOM tag out there. Let's made up something. So let's just say something called date. Is it there? Or date is also there. Just to make sure there's some false return. So we randomly make that some parameter is not there. So this is a way that you can tell whether something is standard DICOM or manufactured DICOM. And if you want to get all the possible tags, you can also do it. So there's a keyword dict under this data dict that will return you with the standard tags out there. And you'll see it's a very long list. And if you look at how many items are there, it's 5,000 something. Yeah. So basically, this dictionary has tag is essentially checking whether that header is inside this dictionary. So it will tell you it is inside this dictionary. All right, so that's probably most stuff. We need to work with the header. We want to look it up, we want to override it. We want to look up some of the, whether they are the standard header or not standard, or the customized or manufacturer based. So the next big part is the pixel information inside the DICOM. And as you can see from the printout there, that's in one of the slot, and we can retrieve that. So that's called pixel array here. And if we assign this pixel array, PyDICOM has this special property that is in lowercase that already converted into NumPy. You can get the pixel array and convert it to NumPy by yourself, but there's a risk of running into errors. So PyDICOM has already done it. So we can look at this array. It should be a two-dimensional array because each DICOM corresponds to one slice in the image. And then we can just plot that out as well. So we get the slice of that array, and we can get off the axis and put a color bar there. So it will end up something like this. This is very rudimentary, and you can get nicer like prints using other libraries or just customize the matplotlib. So here I just show you the very basic way you can just get some information out and verify that's the right thing you get. So array, since it's a NumPy array, then everything you know about NumPy will be useful here. How you flip the data, how you just get to certain rows, like indexing, slicing. So all this knowledge will come to help at this point. So here I just show you some simple things like how to get this gets you the shape and what's the data type out there. But with NumPy, there are much more complicated things you can do to manipulate the data. Right, so that's about DICOM. And just touching about Nifty and the differences between DICOM and Nifty, because in MRI, a lot of the data are in Nifty rather than DICOM, because we sort of getting not from the source, and some people might have already converted that into Nifty. So the main differences are a DICOM contains the 2D plane, so one slice only. So if you have a 3D plane, then you have multiple DICOM files. And how many planes are there, then you end up with how many DICOM files. And DICOM can also have other files associated with it, like a DICOM structure, which tells you sort of you can use it to store the contours. A DICOM plane, if you do radiation planning, that will end up in a plane. DICOM dose, which stores the dose information for radiation therapy. Again, DICOM is a very big thing, and we're just talking about the file structure here. Nifty, on the other hand, stores the entire 3D scan. So when you get the pixel array, that's not called pixel array in Nifty, but when you get that pixel part, it will be an entire scan of itself. Another difference, which can be, you should be cautious, is DICOM usually contains a lot of patient information inside that, especially when you export it from the PACS system. You have patient name and patient age and all this, like patient address, although that's usually not there, but you can see there's a tag there, and you should be careful. So de-identify the data before you sort of share the data. So just do everything you should based on the data transfer agreement. Nifty, on the other hand, doesn't have that much patient-specific meta information out there. So again, you should still double check, but it's just less prone to like patient information leaking. So in practice, you would get data from the PACS system as DICOM and do some pre-processing or wrap it up into a Nifty and save it as a Nifty. So similar to DICOM, Nifty has multi-parts inside it. It has the header, which stores just similar to the DICOM header. It has the pixel array itself, just like the pixel array in the DICOM. It also has the transformation. The transformation defines the affine transformation of where the image is located in the 3D plane, in the 3D space. So when you work with libraries like nibabel, I should put in the hero here. The best tool to handle Nifty is nibabel, in my opinion. So if you use nibabel and you can create a new Nifty data from scratch, and you usually need the header and the pixel array, and you can also pass in the transformation, so it's aware of the where the first voxel is in the 3D space. So that's sort of a quick comparison between Nifty and DICOM. All right, which very fun part, which is how can you create these files? Or if you want to save your data, how do you do it? Well, the best way to do it is to modify from the existing file, because DICOM is very complex. It's very easy that you say save something that looks right in 3D slicer, but when you use it in the another software that is checking, like doing verification on some header, and it's not there because you didn't save it. But it's in the original date, like original DICOM. So just create something by modifying an existing file is usually a good idea. So I'll just demonstrate this. So in our DCM, we just read from PyDicom, we have that instance UID. So we have the patient level, the study level. The second level is the study, and then under study, there are series, and under series, there are instances. So one instance is one slice. And each instance will have a different UID. And what I can do is to just change this UID and then save this as a new DICOM file. And PyDicom engine has some function that to generate this very long UID. And if you want to control, okay, I would want all of this the same, I just want to change the last bit of that, you can provide a prefix. And you can also provide some nice seed, so it will generate, it has some reproducibility out there. But in this case, I don't need that. So I just wanted to start with this. So this generates a new UID and assign back to the DICOM object. So it's in that memory yet, it's not saved. It's in the memory now, but it's not saved to the disk yet. So what we can do is DCM save as, and we have the same file name plus dash modify. And when we do a list now, say, you will see the file is here that we just saved. So another great feature of PyDicom is once it's installed, it has some command line tools out there as well. And you can use these command line tools, say, to quickly look at what's the header, the one of the header, you can easily do it. So if it's, again, if it's the like shell command, you should start with the exclamation mark, because this is not Python code, it's the shell command. All right, so this gets you with a new UID compared with the original one, which end up with 722. This one end up as 671. So this is how, this shows you how you can modify an existing one and then save it. Now, in extreme cases, you can't modify for an existing one, and you think about like creating one from scratch. And this is where the CLI tool can help greatly. So there's a sub command there called codify. So what you can do is that provide the file to codify. Codify will analyze all the headers, all the slots and key and values inside there, and produce the code to create the exact file to you. So what I do here is that I provide this, now the file just save to PyDicom codify. Now, assuming that I want to create this file from scratch without any existing DICOM file, and then I will route the output to another Python file called create DCM. So when I run it, so if you run that, you will see there's a create DCM .py somewhere there, and you can double click to look at the code the codify generates. So what essentially it's doing is it's looping through all the like the header information and what are the keys out there, and then set the right value based on the DICOM you provide to it. And then the only thing it won't do is it won't write the pixel information there, which you need to modify this code by providing what pixel data you want. So usually you have say you have a NumPy array and you want to convert into DICOM format. So you can sort of encode that NumPy array here and then save that as another DCM. So that's the complete code from scratch that you can create a DICOM file. So you can do similar things for Nifty. It's slightly easier with nibable. You just provide the free component, the header, the pixel array, and also the transformation. Okay, and for other like tasks, you can check out the PlatyPy Rob presented on that. That contains a lot of useful things like visualizing the vector fields if you do image registration, things like that. Okay. There's probably not too much time left, and I just briefly talk about. I think I've basically accomplished my goal is to show you a very surgical way to deal with DICOM data. And then anything from now on is probably something bonus, extra information. So in practice, when you build a data processing pipeline, a lot of times you will apply filters to that, and you should wrap these things as, say, function, and as I mentioned before. And inside this function, if you want to carry out certain tasks, usually simple ITK is a very good package to use because it has lots of filters inside that. You can also define custom filter if you want. So I put something here just for you to play around with it, maybe after this session. So the first thing you do, I'll explain it briefly, is to import simple ITK, and because it's not there in the code lab session, you should install it. So simple ITK wraps around the C++ ITK module and expose it as Python interface, so you can call Python with it. And again, simple ITK the data type is by its own. So it's like a image array, but it's space aware, it's location aware. For example, if you have a patch, the simple ITK object knows where the patch is lying in the 3D space. So it's different from, say, a NumPy. A patch is just a patch that it doesn't have any information about the location. There's some conversion you can do between a simple ITK and NumPy. So there's something you will end up using if you process something using simple ITK, then you want to route things into a deep learning model, then you will need to convert into NumPy first, and then from NumPy to, say, the PyTorch tensor, for example. Okay, and I got some example files there as well. And if you run this code, this is quite complex code because it is shell command, but it's doing a loop in the shell command, and it just gets pull things down. Yeah, it's quite complex for me because I'm not very good at shell scripting. I'm basically do everything in Python. And then you can run, for example, some filter like the bias field correction on the image data. Right. I think the last part of that, I would like to talk about the Jupyter. At the beginning, I'll mention that I'll talk about Jupyter at the end of that. Jupyter is basically what we are looking at here. The code lab is just another form of Jupyter, because usually you run Jupyter notebook on your ARM machine, so you can sort of see the output and also the documentation at the same time. And the history of this evolved from the pure Python to IPython. At that time, the Python XYZ, some of the other distributions that has the basic Python, but adds some scientific function to that. So I can show you what IPython looks like. So if I enter Python, it will be something what we plan, like a equals to 1, or name equals to hello Python. And when I type name, there's no auto-completion, and it can't do other stuff like magic functions in the IPython. So it's purely Python. And if I go to IPython, it adds some like other capability to it. So it's a name equals to hello Python again. Again, I can refer to the input like this, and can also get the output from previous sessions. I can do magic commands like this, history, to look at what history I've done. So this is the IPython. Okay, and people say, okay, this is not enough. We need to sort of have documentation and this output all like merge together as one document, so that you can like write the process just simpler to what I've done here, like some bit of explanation and then the code, and then we can execute it and get the output. And at the end, you can just get everything as one page and then share with other people. And then that's how people come up with the IPython notebook. So if we run IPython notebook, they will start a local. Sorry, that's called Jupyter Notebook. That's called IPython Notebook in history, but now the Jupyter, I took it over and we work on that. So currently that function is under Jupyter. So we have Jupyter Notebook. So if we run that, that will open up a new browser, and you might have a notebook file here. So here we can download the whole thing as a file. So the file name is still IPython Notebook. So it's a little bit all mixed together. So if we download here, and then here we will see, we'll see the file is downloaded. Now we can open it locally. And this is the Jupyter Notebook on my local machine. And so I just let you know there's a feature that you can convert this as, I can't remember where it is. But what you can do is you can convert the document as a slideshow. So you can not only have as a one page that has the code and result, but also you can convert it into a slideshow. So you can say click button, click mouse, and it showed up as one cell will pop up, something like that. Let me see when it is. Okay, let's quickly Google Jupyter Notebook slideshow. Okay, so it's view cell toolbar slideshow. View cell toolbar. Yeah, okay, yeah, it's here. So you can select, is this a new slide, or it's a sub slide or fragment? So subslide and fragment are those stuff that you can click the button and then it will pop up. So at the end, you can basically save some time by creating another PowerPoint. You can simply use whatever is already done. Right, so I'll close this. So unfortunately, due to time, I cannot cover anything about AI or deep learning, but this will prepare you with enough sort of information to do all the data preparation. And every NumPy can be routed into, say, TensorFlow or PyTorch. And then you can carry on with the model training with that. And if you use simple machine learning like the sklearn, what I mean by simple or traditional just means before deep learning, say logistic regression, or XGBoost, things like that. You can use sklearn and that support NumPy natively. Well, I'll stop here and see any questions or discussions we can do.